The microphone is actually for recording purposes, so, you know, wherever you are in the room, that's where you will be for posterity on the recording. Good evening, ladies and gentlemen, and welcome to the center of the universe. Is anyone new here tonight? Excellent, welcome. And for the rest of you, welcome back to the center of the universe. We are about, I guess this is our penultimate pre-launch star party, because our real launch for every year is the International Astronomy Day, which this year is on May the 3rd. Let me not keep you because you're eager to hear our speaker, but we start with a land acknowledgement. We acknowledge and respect the Senchothan speaking peoples on whose land the observatory stands. They're the Wasatch people, the Tsatlip, Sekum, Sayout, Paquichin, and Malahat peoples. Their historical relationships with the land and the night sky we share, and we continue to do that to this very day. We are trying to set up some new collaborations with the local First Nations, of which I hope you will hear fairly soon. And for a quick introduction of someone who actually doesn't need too much introduction, I had to ask Bob how many books he'd written, because I've lost count, but apparently the count is 7. Bob, originally from Ontario, has been a Victoria's, how long is it now? Since 2011, wow. He's been working in his job at the CBC for 32 years now for Quirks and Quarks. And tonight he's going to talk to you about dark matter. Or he said he was on the slide. Yeah, all right, okay. So I have a little story. The first time I ever met Bob was when we were a new organization and we were tentatively looking out for potential advisors, and a couple of us decided to meet with Bob in a cafeteria around on Hillside, and we were feeling, we dressed up and were a bit nervous, and we ordered coffee, and Bob went ahead and ordered a beer, and the beer he ordered, of course, was Hoyne's Dark Matter. So, without further ado, here is Bob McDonald.
Thanks, Ben. Hello, everyone. Thank you so much for coming. For those of you who listen to Quirks and Quarks, this is what I look like, okay? You only hear me coming out of the car radio, right? Anyway, I'm delighted to be here tonight. I'm actually on the board of this organization. I'm quite happy to help out to bring this place alive, to bring people up here. Too bad there aren't any stars out tonight, but come back from some of our star parties. So, do you want to hear the latest news from astronomy? We're living in a black hole. We could be living in a black hole. This is the latest. Yeah. It's once again, astronomy is telling us that the way we see the universe is wrong. And it's been doing this forever, ever since astronomy has been around. And I want to take you through a little historical journey about how many times we have had our heads bent by fact, by observation, by astronomical observations. And it goes right back to before there were even telescopes. You go back to the ancient Greek astronomers, the ancient Central American astronomers. All they had was their eyes and their senses. And if you look at the world through your eyes and your senses, it looks flat. The ground is always down. It doesn't seem to move. The sky is always up. If you drive any direction long enough, you will come to an ocean. We don't have to go far here, but you go that way, you'll find one. Go this way, you'll find one. Go any direction, you'll find an ocean. So it looks like we live on an island surrounded by a circular sea. And that ocean, when you look at it, has a very sharp edge that you could fall off. The sky looks like a dome. It's blue on one side and black on the other, and it rotates around us. The sun is stuck to the blue side, and the moon and the stars and the planets are stuck to the black side. That's what it looks like. And that is why some of the early models of the universe, like this one, shows just that. And what's holding us up? Well, let's give it to the great beasts on the backs of giant elephants And they're on the back of a giant sea turtle that's swimming in that endless sea, and the sky is just a big snake biting his own tail. We have more modern versions of this now, artists. And are there any flat earthers here, by the way? Damn. I have some questions for flat earthers, you know, because here's the flat earth model. I don't quite get it, but I want to know, one, where's the South Pole? And two, how come there's never been an expedition to the edge, to look over the edge and tap on this dome? I'd like to know what it's made of, if it can be that big. So anyway, so we have people, flat earthers only believe what they can see. So if you only believe what you can see, that's what it looks like. But this is wrong. This is not the way the world really is. And it took a while for us to figure out that we live on a ball. And the very first measurement, the very first person to measure the Earth and find out how big it really is was this guy. His name was Eratosthenes. He was a Greek mathematician about 2,200 years ago. And he was also the head of the Great Library of Alexandria, which was the largest library of the ancient world. It had the gathering of all the knowledge of all the civilizations ahead of time. Now, the Greeks believed that the Earth was round. I mean, why not? The moon's round, the sun's round, why not the Earth? But they didn't know how big it was. But Eratosthenes measured it. And here's how the story goes. So he was the head of this big library, what we think it looked like, but this isn't where he lived. The Alexandria is on the Mediterranean at the mouth of the Nile River. But he lived in a little town called Syene. Do you like my map? Okay, so here's Alexandria, the library. Here's his town. It's now called Aswan. There's a big dam there, okay? So Syene. Now, he knew how far it was from Syene to Alexandria. The story goes like this. On June 21st, Eratosthenes was home in his hometown, and there was a water well in the main square. A lot of these towns had them. At high noon, and I don't think this was an accident, at high noon, he went and he looked down the well, which we all do, right? You come to a well, you want to see if you can see the water in the bottom. Not only did he see the water, he saw the sun shining in the well, which meant that the sun was exactly overhead, straight up. So he thought, now this is June 21st, summer solstice, right? When the sun is the highest. So he thought, if the Earth's flat, you should be able to look down any well on June 21st and see the sun, because sunlight comes down in parallel lines, right? But if the Earth is a curve, if you're in another spot from Syene, you should get an angle. So here's what he's looking for, okay? He's looking for an angle, a piece of the pie of the Earth. So he waits a year. He goes back to Alexandria, but there's no water well. So instead, to measure the angle of the sun, he goes outside the library and he puts a stick on the ground. And the stick is shaped like an L. It's called a gnomon, and it makes a shadow. It's the same piece that's in the middle of a sundial, but it has a scale on the bottom that'll tell you the angle of the shadow. Now, I've been to Alexandria, and they have a new library there, and they do it now with kids. Eratosthenes didn't have water bottles like this, but they do this. They do this with the kids, and they measure the angle of the shadow. So here's what he did. He goes outside just before noon. He puts a stick on the ground, and he watches the shadow. If the shadow goes to zero, if it disappears, the sun's straight overhead, the Earth is flat. End of story. Well, of course, it didn't. It went down and down and down, then it stopped at 7 degrees. 7 degrees, and it went back up again. So he's 7 degrees over the horizon. A circle is 360 degrees. 7 into 360 is... There are three kinds of mathematicians. Those who can count and those who can't. Think about that. Okay. It's roughly 50. It's about 50, okay? 50. So he's got 1/50th of a circle. So that means that the distance between Alexandria and Syene is 1/50th of the distance around the world. Well, he knew the distance. He could probably do that in his head, and he came up with a number that was exactly right. And what's astounding about that is that this was the known world at the time. This was the known world in his time. The Mediterranean, a little bit of India, that's about it. They hadn't discovered the rest of the world yet. Can you imagine going back in time? I mean, if I could travel in time, I'd like to meet him right at that moment. You know, hey, what are you doing? I'm measuring the Earth. With that, yeah. Okay, so how big is it? It's really big. It's really big. So he discovered that our ignorance is greater than our knowledge. Our ignorance is greater than our knowledge. It's far bigger than the known world. So imagine showing him this picture. And by the way, this was the last picture taken of the whole Earth by a human being. This is from Apollo 17, the very last mission to the moon in 1972. They were the only mission to get a full Earth like this. And on the way back, they took this shot, which has sort of become the poster child for the environmental movement. But look, here's Africa, there's Syene, there's Alexandria. Isn't that poetic? Isn't that poetic? I love it. Anyway, so Eratosthenes finally told us, yeah, the world's a whole lot bigger than we thought. Well, now we get on to looking at the sky and how the planets move. And they didn't make sense because planets move among the stars. Sometimes they back up, then they go ahead again. They were trying to figure this out. And a fellow named Ptolemy came up with this model called epicycles and deferents. What's the deferent? Well, that's the difference right there. Okay. So it's this weird situation where the planets are on their own little cycles as they go around us because we're in the middle, because we're so important, because it looks like we're in the middle, because everything goes around us. And the problem was, this model gets really complicated when you start incorporating all the planets in the solar system. Plus, it doesn't work very well. Then, another ingenious fellow comes along called Copernicus. And Copernicus figured out, you know, there's a better way to do this. Instead of putting us at the center, let's put the sun at the center. It's a lot easier. But that wasn't a very popular idea because it doesn't look like we're in the center, or that the sun is in the center. It looks like the sun goes around us. It rises in the east and sets in the west. We're not moving. But then another fellow, Galileo, comes along with a telescope. And his telescope, you know, people think he invented astronomy. His telescope was to look at ships. He was trying to sell it. He's trying to manufacture a telescope to sell it to sea captains so they could see other ships on the horizon, tell what their flags were. But he pointed it at the moon, and then he pointed it at Jupiter. And he saw what we see here, that you can see with our small telescopes or a good pair of binoculars, that on either side of Jupiter are these little dots. One of them there's in shot. But there's 4 dots that go around Jupiter. And he watched them from night to night. These are the Galilean moons. And he saw that little things are going around a big thing. Little things go around big things. Okay, so our planets go around a big sun. I can't wait to tell the Pope. Unfortunately, the Pope was an amateur astronomer, and popes don't like to be told they're wrong. So Galileo paid for that. But he was right. The first empirical evidence that, yeah, planets move based on this model. Okay, so now we got our solar system straight out. Isn't that nice? It's all great. So we know our place. We move, and we're moving pretty fast. Then Edwin Hubble comes along, and he's interested in the Milky Way, our galaxy. And he's looking out, and at that time, our Milky Way was called an island universe, because they thought everything in the universe was part of our Milky Way. And I can understand that because it is huge. It's huge. If you want to go from where, oops, sorry, too far, back. If you want to go from where we are here to the center, it'll take you about 30,000 years at the speed of light. If you want to go from one side of it to the other, from here to here, that's 100,000 years. And it's got 200 or 300,000 million stars in it. That's, if you turn stars into grains of sand, it would cover this floor. It would cover this floor about that deep. Big dump truck full of sand. That's about our Milky Way galaxy. Well, Hubble found out, through very clever techniques that I won't go into, that the Milky Way is not alone. It's not an island universe. It's interesting, but there are other island universes out there. And this is a major discovery. The universe is a whole lot bigger than we thought. We're not everything. Our Milky Way isn't all there is. There's other galaxies out there. And he, and along with another astronomer, Lemaitre, discovered that all these galaxies are moving away from us. the universe is expanding. And it's expanding in a very strange way. The farther away galaxies are, the faster they're moving. That doesn't make sense. Usually, if you have something like fireworks, everything goes, and everything goes out at the same speed, right? The universe isn't doing that. It looks again like we're in the middle. The farther away you look, the faster it's going. How can that be? Well, this helped us figure that out. He said, the galaxies are not moving through space. Space is getting bigger. Space is expanding. Huh? Let me show you. I have a model of the universe. I need 2 volunteers. Would you 2 like to help me out? Okay, come on up. Can you take that in? Would you like to help? Sure. Okay, stretch back. Here is my model of the universe. Now, every dot is the same distance apart, okay? Now, can both of you just kind of stretch it out? Okay, you move back, you move back. You'll notice that the dots get farther apart, but they're not moving on the rubber, right? Okay, bring it back. Okay, come on back. Good, okay. Now, let's suppose that I'm on this dot right here. This is our galaxy. Now, you stand still. Okay, now you move back. Can you see? Okay, just keep coming out and back. Coming out. Keep it tight, but keep coming out and back. You can go faster than that. Okay, can you see how the one on the end is moving a whole lot more than this one? That's the idea. That's the idea. It's the stretch. That's why we're seeing this. And here's the interesting part, okay? If I'm over here, okay, now you stand still. Okay, now you pull that one. Now, that one's moving faster. So everyone feels the same thing. It doesn't matter where you are. You're going to think that, okay, hold it. You're going to think you're not moving and everything else is. So everyone gets the same perspective. So imagine that in 3 dimensions. Thank you very much. You were very good cosmic helpers there. I invented that. I had to go to a senior citizens exercise house to find it. It's okay, I'm a senior, I'm allowed to do that. So this was the thing, space is expanding. All right, well, we get our heads around that. Then this fellow comes along, Fritz Zwicky, and he asked himself a question. He said, we have all these galaxies out there, and some of them come in clusters. They tend to come in groups. We're in a group. We have ourselves, Andromeda, and a few other galaxies. We're all together in a group. He thought, how much gravity does it take to hold galaxies together? Well, gravity depends on mass. The more mass you have, the more gravity you have. The Earth is bigger than the moon, so there's not as much gravity on the moon because it's smaller, right? So he added up the mass of a bunch of galaxies, and he calculated how much gravity that gives, and there wasn't enough. By a long shot. There wasn't enough gravity to account for them. They should be flying apart. Then later, Vera Rubin, there's a new telescope being built in her name. She did the same thing with one galaxy. She said, how many stars are in the galaxy? How much gravity do you get? Why doesn't it fly apart like a lawn sprinkler? And she came up with the same result. There isn't enough mass to account for all the gravity that's there. So there must be some mass there that we're not seeing. It was called the missing mass for a while. Now it's called dark matter. And when scientists say dark, that's a very technical term for, I don't know. We don't know what it is. We don't know what it is. But it makes up about 25% of the universe. 25% of the universe is dark. We don't see it. And the other thing that we have found since then is that, here's an example of how you can see dark. And see these arcs here? Here? Looks like a circle. This is called gravitational lensing. And that's where gravity bends light and makes it act like a lens. So we can actually see things farther away than we normally would. But again, there's more matter in this, keep hitting the wrong button. There's more matter in this cluster of galaxies than can cause that effect. So there's darkness. There's something here in the dark that we don't see. Now, thanks to the new James Webb Space Telescope, which was sent up to discover things we didn't know, and boy, has it delivered. One of the things that it has found, as it looks way back to almost the beginning of the universe, to 1 billion years after the Big Bang, which is really close. The universe is 13.8 billion years old. Webb sees back about 1. And it sees these galaxies that are quite well formed, way, way back in the early universe. And this doesn't make sense. We have models of how we think galaxies come together. We think they start out as amorphous blobs, and then they evolve into the beautiful spirals like the one we live in. What are these spirals? What are these developed galaxies doing back at the beginning? Does that mean our model of the universe is wrong? Probably. It's called the Hubble tension. The Hubble Space Telescope saw the same thing. What we think is the age of the universe isn't what our observations are showing us. There's a difference. So we're having a problem with that. There's something going on that we haven't quite figured out yet. And one of these things is dark energy. So dark energy was discovered in 1998, and it's the idea that not only is the universe expanding, it's speeding up. Something's causing it to go faster. We don't know what that is. It's dark. And by the way, those two things, dark energy and dark matter, they make up 95% of the universe. So what we see, when you look up in the night sky and you see the little dots, that's only 5% of what's really there. We think we're so smart. We think we're so smart. We think we have it all figured out. 95% of the universe is unknown to us. So when you look up into the dark sky, look at the dark. That's really what the universe is made of, and we really don't know what it is, or if it even exists. Maybe it doesn't exist, because the latest has come from this idea. When you look at the universe on the largest of scales, you see a cosmic web. Matter, these are all galaxies, okay? These are stars. This is looking at the entire universe. So stuff clumps together in these filaments, and there are empty spaces between them. So you get clumps like this, and there, and there, and there. But then you get these dark voids down here, down here, down here. And there's a new theory that replaces dark energy. It's called timescape. Timescape. And this gets us back to Einstein. Are you still with me? You okay? Okay, this hurts me. This hurts me a lot. I just found this out this week, okay? So I'm learning about it. Timescape goes back to relativity, because Einstein said that if you're in a gravitational field, if you're in high gravity, time slows down. Time slows down. So that means that clocks are running at different speeds. If you're in a cluster like this, time is running slower than it is in a void like that. Time is running faster here and here than it is there. So these will appear to be expanding faster because time is going by faster there. It's an optical illusion. That's the idea. It hasn't been proven yet, but this is the kind of debate that's going on in astronomy right now. Is it an illusion? Is it because of time differences, or is dark energy real? We don't know. But what's interesting about dark energy is that it's the only force we know of that goes against gravity. No other force goes against gravity. So it's pushing the universe out. So that's all I know about that. And I think that's about all anyone knows. And then finally, what I started out with, this is just recent from the James Webb Space Telescope. They did a big survey of the sky, and they found that 2/3 of the galaxies, the distant galaxies, are all spinning in the same direction. They're all spinning in the same direction. And this would suggest that the entire universe is rotating. Because if you think about something big that's rotating that then condenses into something small, whatever that small thing is will conserve that rotation. It'll be still going in the same direction. So our solar system started out as a big cloud that was rotating, and then it condensed down on the sun and the planets. Well, the sun rotates and the planets go around it all in the same direction. We're all going counterclockwise. So this suggests that maybe the universe is rotating. Well, what was before that? Well, we know that black holes rotate. So is it possible that we are inside a giant rotating black hole, that the Big Bang emerged within a black hole. Now, there are calculations that have been done that if you add up all the mass of the universe and the size of it as we know it now, it adds up to a black hole. So maybe we're living inside a black hole. We can't get out, but we're in it. That also means that all the other black holes that we see in our universe are windows into even smaller universes within them. And on ad infinitum. I love it. We're so messed up right now. We think we have it all figured out. We don't know. We don't know. And I find that exciting. I find that exciting. Our ignorance is still greater than our knowledge. And that means we have more to learn. And we have more to study and figure out this place. And to think we've got it all figured out, nah. Astronomy's probably going to come along. Some great thinker or a new instrument or whatever is going to tell us that what we think we know today is not quite right. And I'm okay with that because I like learning. I like learning about new stuff. So stay tuned. Stay tuned. But the final thing I want to show you is that we have figured out a lot. We have figured out a lot. And one of the things that we do know is that in this great universe, this is it. We have yet to find another one of these. We're up to, what is it now, 5,000 planets going around other stars? They'll all kill you. None of them are like the Earth. They're interesting, but they're not like the Earth. All the planets in our solar system will kill you. Yeah, people can go to Mars, but there's no oxygen. There's no ozone layer, so ultraviolet light gets to the surface. It's cold. It's deadly. You have to be in a habitat or in a spacesuit the whole time. So yeah, we can do it, just like we can live at the South Pole. But it's not this. It's not like Star Trek. I love Star Trek. But one of the things that bugs me is every time they go to a planet, it's always a really nice day. They're not wearing space. They don't even wear sweaters, for God's sake. English. Not like that. Just think we're even here. And this is it. So let's take care of that, okay? Thank you so much for coming here tonight. Thank you. Thank you. Oh, yeah.